Okay. Hi, everybody. Today we shall continue our work regarding regression of nonlinear multiple functions by using LabVIEW. We shall illustrate three different virtual instruments to understand how to configure and how to design the program. Remember, in the previous lecture, we used the same function, which is called nonlinear fit, but it has two instances. The first one, which is nonlinear curve fit LM, and the other one, nonlinear curve fit LM formula string. We worked with the second instant. Today, we shall work with the first instant. The difference here is that when working with the previous instance, we have to define the fitting function, and this function must be as close as possible to the real trend of the data set, which is used in the program. Here we are not going to write such a function. We are going to build a sub-virtual instrument and save it in the memory, and this main program will call it when it is initiated. So at first we need to know some information about how we can write this model function and save it. For this purpose, in LabVIEW, they designed a special template, and they recommend only to work with this template in order to create the model function. Let me show you how to go to it and see it. If you go, or here, if you click on the let me drag it. If you click on the bottom help, and now you go to LabVIEW help, and then type here in the words, using the words which is going to be used by search, I have typed nonlinear curve fit LMVI. I have got a list of topics here. The most interesting for me now thing is nonlinear curve fit VI. I want to know about the same function because this is my target now. I double click it now. I have, as you see, this picture where we can see the inputs and the outputs of the main virtual instrument, nonlinear curve fit LM. Here you see you have to select the instance which is required, either the first one, nonlinear curve fit LM, or the second one. I have to select the first one. Now we are here. Now, if you study the information related to this virtual instrument, you will see here this input function of xi, f of xa, I'm sorry, where x is the array of synthetic data which will be used when implementing this function. And A represents the initial values which will be used in search. But you will see also that this input is a reference to the VI that implements the fitting model. So this will be the output of the fitting model. This will be the output of the fitting module. And in order to construct the fitting model, we need to use this template. To open it, you can double click it, as I did here. And now you see that this template has an input A. This is an array, one-dimensional array, which will include the coefficients. They may be 2 or 3 or 4, depending on the character of the function. And this is the x, which will include the data set which will be used by the program. Another input is called data here. You will do nothing with it. And the other one is output control. These 4 objects will be assigned to the left 4 terminals of the pattern configuration, which exists at the upper right corner of the front panel. So the first block here represents A, is connected with A, assigned to A. The second one is assigned to X. The third one is assigned to the data. And the fourth one is assigned to the output control. The left side terminals, the first one is assigned to the function which will be at the output, f of xa. The second one is assigned to f prime of xa, the differential. And the third one is the error output. Important to note here that you have to assign these 4 input terminals and 4 output terminals when you try to plot or to configure the function or the block diagram of the function. The block diagram is prepared for you also in general as a frame. Here you have this for loop, and this is the input A, which will include, you can here index this array, and you can use the first element or the second or the third or fourth, depending on the number of coefficients which are going to be defined. And here is the data which will be used by the system. The output will be f of xa and f prime of xa if it is needed. But you can work with f of xa only without the gradient here or differential of the function if it is not needed. In order to work with it, what you have to do only to have a copy of it, and you paste it on a new VI, Then there you create your model function and save it at a given position in the system. Now you will work on it and decide how to call it by the main program. Let us go out of it now. It is not needed by us. Now, if I go to my program, here, let me make it at full screen. Here is the main function. Here you see, here I'm sorry, this is the sub virtual instrument which represents the model. What is done here? I have only dragged the icon of the submodel and positioned it here. Here you can see the terminals of the model function. The first one will be A. Look, it is A. The second one will be X. These two terminals for the data and the control output are not connected, not needed. At the output, I have connected f of x of A, which is needed by me. So, by dragging this icon here, I can supply it with the parameters, values of the parameters which are going to be optimized, and with the synthetic data which represents an array of values which will be used by this function. The output now is here f of xa. Remember, in the previous lecture, when we worked with the second instance here, the input y was composed of two components. One of them is the function which was created as a string. Here it is not as a string, here it is as a block diagram. I will show you it now. And the other component represents a noise added to the useful signal here, so that the output y will represent as if it is a real measurement values with some noise. So we are doing generally here the same as we did in the previous lecture. Now what I have done here, I double click it to open it for you. Now this is the front panel. I go to the block diagram and we see this is the input A. As an array, I have indexed this array index. I have now 4 parameters, 4 values, which are going to be used by the program here. And also I have furnished or connected the array X here, which is going to be indexed by the for loop and used according to the program which is given here. In this program, as you see, I am using the exponential function and the sine function, so as to formulate the module function or fitting function. The fitting function, both of course generated values here are summed together and are given as the output here. This is the output f of xa. If you go to the front panel here and I run it, you will see this configure, which is a damping, somehow damped sine wave. Because as you see, the heads are practically resemble an exponent which is going down. So this is the model function which is created, and now it is outputted here. Here we have 4 inputs. This is A. If I double click it, you will see how it is marked here as A. If I double click the second one, you will see it will, sorry, it is the X. The third one will be the data, and the fourth one will be the output control. To the right side here, the first one will be the output. This icon here is the icon which I dragged. I can drag it. I press on the control of the computer, put it here. Sorry, I cannot put it here. I have to put it on the block diagram of the main program there. It should be beside it. Or I can copy and paste it. There is no problem. And now I have the following picture. The main virtual instrument, the sub-virtual instrument, the sub-virtual, sorry, here the sub-virtual instrument, the output of the sub-virtual instrument with an added noise represents the Y values which is supplied to the function. The second, which is X, here, this is X, as you see, it is the output of this generator, where we used the ramp function, ramp pattern VI, with a given number of samples. So the output is an array here, and this array is supplied to the sub-VI, and the array is also supplied to the main program. Here, if you see the noise, here it is really composed of 2 noise elements with Gaussian white noise. And as you see here, the standard deviation of each of the noises is 0.1. Number of samples here, it should be about 100. It is 100. So when I take the output of the first one and the output of the first 2 and create an array here, and this array is concatenated, I shall have here an output, a one-dimensional array, but the size of this array will be 200. This is why I made the size of the ramp function here 200, so that they could be matched together at the input. So the number of elements of the X and the number of the elements of Y is the same. It is 200 samples. The system must work with this configuration. Now, how to, okay. An alternative way to do it, as you see here, we can use another noise data taken at the output of a uniform function here. Continuous random VI function. This is found also in the mathematics palette and could be connected directly here instead of using these 2 elements. But remember, the number of elements here must be 200, so that to be the same as with the input array here, if it will be used with it together. I will show you a little bit later. Now I shall talk with you also about how to configure the calling process, how we call the sub VI by the main VI. If you look at the program here, you find this input f of xa terminal here. In order to create a static reference VI, let me write for you the model itself. What you have to do, first let me cancel it. Now I don't have anything. You have to go to the application control palette, select from there the static virtual instrument reference and locate it on the block diagram. Then you go to the icon of the model function and drag, sorry, I dragged it. I didn't put my finger on the control. I have to press the control and then drag it here. And now it is there. Now if I connect it, it will show an error. No connection. Why? Because when making static reference VI, it should be referenced strictly. This means that the terminals must be exactly the same here and at the model function. To do that, I right-click it here. I right-click it and go here and press strictly typed VI reference. Now this, as you see, star appears here, indicating that the connection is correct. Now if I connect it with the terminal, everything is okay. This is not necessary for me. I will work with the previous one. So now we have created a static reference which is strictly connected. We have guaranteed that the terminals are exactly the same. In LabVIEW, you have really a lot of work concerning calling the sub-VI. You can call it dynamically. And the dynamic call also has many modifications. One of these modifications is to call by reference. Call by reference. To realize this is already done for you. If I cancel it here and I connect the output of the call by reference here, it should connect normally, no problem. But how to do that? I want to remind you with it also. You have at first to go to the application control, then go to the static VI reference and place there the static VI reference. Then you go again to the application control and place open VI reference. This one. This is, if you want to see it, it is open VI reference. And this is a static VI reference. Now, I should connect the path, a path which connects between this element and this element. I right-click here and go to create property for VI class and select VI path and place it here. Now, if I connect the reference with it, it is connected. And if I connect the path with the path here, the path is the second terminal, it is connected. In order for the system to work as a dynamic call, so I have to call by reference. I have to go back here, call by reference, and place it here. And then I connect the output to this. As you see, it doesn't work. It gives an error here. Why? Because nothing is inside the static one. I have to move or to copy this VI and place it there. But still, there is something wrong. I have to strictly connect it. Now it is okay. Now I go here. Here we have a terminal called type specifier VI refnum. I right click it and create a constant. And again, I drag my VI there. Now it is created. The last thing to do is to connect between the output here and the input here. Why I am telling you that? Because you may need this configuration also. The first configuration is easier to work with, but this one gives many different modifications of using a call between the sub-VI and the main virtual instrument. It is not our target in any way in this lecture. I wanted just to show you it. So we can connect now this terminal here and work with it, or connect it from here and work with it. One of them is sufficient. Now we have realized a static strict call between the virtual main instrument and the sub-virtual instrument. After configuring all these things, what do we need? We need to plot, of course, the input, which is y, with reference to the independent variable x, and also to plot the output with reference to the already generated fit or predicted values. So this is the predicted values, and this is the x. And here we have the x itself with the y at the input. And now we can create an array of both and use x, y, sorry, I should go to the front panel there, to the graph, and select from here the x, y, and put it here. It is already here, so I just wanted to show you. Now here, as you see, in our case, I have this figure which represents the original curve, the model function, which is generated by the sub-virtual instrument. The red curve here represents the fitted values, the predicted values for this raw data set. If we consider the quality and the performance, I have also there created the goodness function, goodness of fit, to see the R squared value and the RMS value. They are here. The RMS value is about 7.5. It is not that high value, it is good. And the R squared value is 0.366. I have selected the coefficients exactly as those which were used in the previous lecture. So as you see, the goodness here is as 0.33. There it was 0.38, if you remember, by using Python. So they are giving practically the same value, and you remember the wavy character of the fitted curve or fitting curve. In Python, it was here, I didn't notice it, it was about 0.38, here it is 0.36. The RMS value here is 7, here it is about 2. There is no difference. Practically, we are getting the same, let me say, results. If we go back here and disconnect this noise component here, and instead of it we connect from here, we shall get, of course, another picture. And it depends on the value here of the let me see it. Here I press on help, context help. If I put the cursor here, you will see it is number of samples, X minimum, X maximum, and the seed. So I have given the minimum and the maximum between 0 and 1. The seed is 42, so that I can get repeatability of the output, because here this function works by using random function, and that's it. So if you go back now and run the program again, we will get, of course, a different picture, and we will get a different performance. The performance here is 0.23 instead of 0.3. It was 3.3, I think. If we want to improve it, we have to minimize the effect of the noise. So if you go back, instead of, for example, 0.1, let me write 0.05, for example, and go back now here and run the program again. It is improved to 0.4, but it is not that good also. So the RMS value is practically the same. It doesn't change, which means okay. Let me tell you one thing also. You mostly have to depend on the RMSE value and not on the R square value. And I have explained to you one day that this criteria may get a negative value or may get a very high value, which is relative to the situation. Anyhow, it is useful, but we have only to take care of the RMSE value. They are the same. But in order to minimize them also more, I can try here. Let me write, for example, 0.001. Sorry. Okay, well, it was 0.24. Now how it will be? It is 242. So what I can manage also, I can manage the value here. Instead of 1, let me write half. and run it back. Now it is 0.28. It is closer to the previous case which we have here. So this is just to show you how you can manage the VIs, what the performance you can tune it upon request and to the satisfaction values. If you now remember the initial parameters which are given here, I have given them these values. I can change them, of course. Let me go back in order to compare between the results. Let me go back and disconnect this noise source with the previous one. And now, if I go back here and run the program, I shall get the first result. Now, let us see the detected values of A and B and C and D, the coefficients. Here are best fit parameters. The input here is given 5. It is predicted as 4.5. In Python, it was 3.8, if you remember. I quoted it for you. This one is minus 0.67. Here it is minus 0.65. It is very close. Here it is also minus half. Here it is minus 0.3. It is close. Here also. So as you see, they are acceptable values and everything is normal. If I change the initial values here, but not so far from the values which are really given convergent, so I usually shall get the same best fit values here and they will not change. And if they will change very slightly and the change will be insignificant. Suppose here, instead of 17, I have put here 8, as I did before. And instead of 6, I have put 5. And instead of 5 here, I have put 10. Now, remember these values. 4.53, for example. If I run the program, now it is about 4. This is practically the same as here, minus 6.5, minus 6.4. So, as you see, this means that the system is working well. There is no problems with the system, with the structure of the program. And the matter is how you can tune it to the extent which is acceptable by you. Okay, I think we have discussed every detail with this program. Let us go to another application to demonstrate it to you. Okay, so let us go out. I do not save anything, I keep it. I go out from here, it is not necessary for me now. Okay, let us go to another program here. Really, I have prepared for you about 6 programs, but I cannot cover them all. I shall try to cover another 1, 2, and that is sufficient. There is no serious difference between them. This one was number 744. Let me show you 745. Okay. Remember, the first function was created as a sign or damping sign. Here I have created, as you see, as a curvature with maximum and minimum and maximum and minimum. You will go to the block diagram. Here is our function. nonlinear curve fit LM. This is the sub VI which I have created. This is the function which I created, and this is the block diagram of this function. As you see here, we have an array of values here, which is fed to the multiplication function, and this will be multiplied by the output of the cosine function. The four elements, X and A and data and output control, are existing. Here they are. And the output here also we have f of x, f prime of x, and the output error. So the system is according to recommendations. Now here we have the function. It is not necessary for me. I have just wanted to show you. Of course, I have here given its name. As you see, as you want, you can write whatever you want. If you double click it, you can see SHG I have written, FIT, okay. Now I go out, back here. So again, I have dragged the icon from the sub VI and placed it here. I have connected it to the coefficient array with the data x. The output is f of x added to a noise. Now the output is fed to the program. X also is fed to the program as I did before, nothing new. The new thing here is I have created a dynamic call for the sub VI and connected now the dynamic call to the appropriate terminal f of xa. Nothing new. If I go back to the front panel and I run it, we will see here the best fit parameters are here. 1, 2, 3, 4 parameters. The initial values are given here. These are the predicted values. Now, if I change these values, as I told you, to a great extent and far away from the convergent values, the system may give an error or give a message that it cannot solve the problem. But I selected values which are not so far. Here, for example, 1 minus 3, 2, 3. It is this selection. I put here 1 minus 1, for example. 4, 1. Now, look at the value here, 2.5 minus 0.5. If I run it, they are the same. They do not change, which means that everything is okay. Of course, you can put any other number. Here I can put 5, for example, and I am sure it will give the same number. Nothing has changed. Just I have fixed some numbers so that not to spend much time, but correctness of the program is shown by the tick here. You find it that everything is normally configured. The R square here is very high, 0.98. It is about 1, which means it is very accurate. And the RMS also is very small. It is about 0. So the work is very nice. Anyhow, we can change, of course, the equality by changing the noise value. Instead of .half, for example, let me put 1 and have a look now how it will look like. Now it is different, and the goodness of the function will be different. It is now less. It was before 0.97, now it is 0.93, and the RMS now is 1, it was about half, so it is, of course, the accuracy decreased. But although the system is working, and this is an answer which could be used in real life. Of course, you can add more noise and you can investigate it by yourself. For example, let me put 2 instead of 1. And now it will be submerged by the noise, the useful signal. Yes, as you see. But look how it is positioned. Really, it is the optimal distribution for it. And the R square is still very accurate and very acceptable. 0.078 and the error RMS is 2.1, which means the system is working very fine and everything is okay. Okay, we finished with this example. Let us move to another example also. Let us try to see the next one, 746, for example, if it is there. Here it is, 746. Yes, it is this one. Okay. Here is nothing new for you because I have just also used static call instead of dynamic call, and I have kept everything the same just to show you. So I will not stop on it. I will go to another. Okay, let us try it to be sure that it's okay. If I run it, as you see, the quality is also the same, 0.98, 0.5, no difference at all, because just I have changed the way it is called by the main program. So let us go to another program. Let us see 750. Okay. This is a rising exponent, as you see. The block diagram is a little bit more complicated. Here is the main calling virtual instrument. It is working in the first instant position, nonlinear curve fit LM. This is our sub VI. The sub VI is, of course, now different. Now, as you see here, it is not shown to you. In order to show it to you, I run the program, go to the front panel, copy, go to data operations, copy data, and now if I go back, it is shown. So as you see here, this is a rising exponential function, or as a power function. We wanted to configure the parameters of it. I have taken 2 parameters. The system, the model is okay. The block diagram, as you see here, has these elements, the data, the XA as usual, the output as usual. No problem. Here is the formula which represents this function. No problem. Here I have taken, at first it was functioning by using a constant 2 instead of this input. I can cancel this input, really, and then minimize the function. And here I put 2, constant 2, for example, and connect it here. And now if I go back and run it, it should give me the same thing. Yes, this is the same thing here. This is now the block, the front panel and the block diagram of the function model. This is the icon of this model, which will be dragged and put on the main block diagram. So I go out from here. And now this is the dragged function, as we have done before. It is also, the setup is exactly the same as we did before. What's new here? I have also added another function of LabVIEW in order to make curve fitting by using exponential fit VI in order to compare the results. Here, if you go to the mathematics fitting, and you will see exponential fit VI. This VI which I have used here. It is just used because the character of the curve is exponential, and it will give results which could be compared with the results we can get from the calling virtual instrument here. This virtual instrument gives 2 outputs. If you put here the help to the context help and look at the output, we see that it gives you an amplitude output here, the amplitude, a value, and the damping value. These are the 2 values of interest which characterize the fitting. And if you want the array of all values, the predicted values for the function here. So these 2 values of interest for us, and the same thing, the values of interest at the output here will be these 2 values. So if you go and look at them, these are the values of the coefficients which we get as a result of regression by using the multivariable nonlinear regression, and the other values which we get by using exponential fit. Here they are. Let me see. Yes. No. This is the output. I do not want the output. I want only the coefficients, the amplitude. Yeah. This is the amplitude. Here you see, look, the amplitude 5.95. Here it is 5.96. They are practically the same. Here, the other component which represents the power is slightly different than this one. But if you consider the MSE, you will see that it is about 82. Here it is about 6.4. This is the root mean square. It is about 40. Here 82. And the coefficient R squared is about 0.9, which is very nice, which is really very nice. If let me go to the block diagram and see. Here it is. These are the coefficients here. Sorry, I'm not looking for this. I'm looking for the goodness. I have this goodness here checked. This goodness is for the exponential fit VI. As you see here, I didn't do it for the function here. Let us try to do it to see how it, if you go to the mathematics, fitting, advanced curve fitting, goodness fit. Of course, I could use this directly and drag it here and also work with it, no problem. I have to connect with it the input value y. This is y, this is y, this is y also. So I can take y here. And y predicted is the y which is here. Yes, this is the y predicted. And now let us see r squared as an indicator. And the RMS as an indicator. Just to see how they are, not more. So if I double click it here, here they are. This is one of them, this is the other. If I run the program now, there is a problem here, none. What does this mean? None. This means that there is no compatibility between the number of the value of the size of the arrays which were fed to the component here. They should be somehow treated. Okay, I will not work with it now. Let us go out of it. Fit, exit, don't save. And I think with this, it is time to finish this program. And we shall continue our work as usual in the coming lecture. Goodbye and have a nice day. Bye for all.